to write equations of and graph radical functions and determining domain and range. I just realized we missed the vocab, so let's jump back to that. A radical function is simply a function with a radical expression. It's got to have a variable under the radical sign. So there's all sorts of roots. We looked at different roots. We're going to be focusing on square root functions. My example here is a cube root function. All right, so back to notes. We're going to take a look at graphing the parent function, and then if you remember when we did the quadratics, we used the parent function to graph transformations. So we're going to do the same thing with the square root function. And we're also going to take a look at the domain and range of the square root function. So the first thing I want you to think about is making a t-table. And the values that we want to substitute for x should be perfect squares, because I definitely don't want to evaluate the square root of 5 and try and graph that. So I know 0 is a perfect square, 1, 4, and 9, and that's all that will fit on my graph. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. Now when we're looking at a square root function, we do not look at the possibility that when you take the square root, you can get a negative answer. And I'll show you what that graph looks like now that I cut my graph in half, so that we won't be able to see all those points, but I'll estimate when I graph them for you. So first of all, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So what the square root function ends up looking like is half a parabola turned on its side. If we were to graph both the positive and negative values, well, square root of 0 is still 0, there's no negative 0. Square root of 1 would also be negative 1. Square root of 4 could also be negative 2. And square root of 9 could also be negative 3. So when we graph the other half of the parabola, what would happen is it would fail our vertical line test, because there's 2 answers for each input. So again, for our square root function, we're just looking at the red part of my graph. We disregard the blue part of my graph. Oh, sorry, I missed domain and range, so let's take a look at that quick. So taking a look at, again, just the red part, so I'm going to erase my blue part so we don't get thrown off by that. When we look at just the red part, think about the input for a square root. We can't take the square root of a negative. And when you look at my graph, notice how I did not put an arrow beyond my 0, because we can't take the square root of a negative. So our domain is that our x value must be greater than or equal to 0. And looking at the range, the output, again, we're disregarding that possibility that the square root is negative in order to look at it as a function. So our range is y is greater than or equal to 0. All right, so now we're going to use transformations. So if you think about, and for those that didn't have me first try, I'm going to go over my analogy real quick. What I do is I show a clip from Batman and Robin. It's a lot more interesting to see this than hear about it on a video. And I show the part where Mr. Freeze is taken to the asylum, to Arkham Asylum. And we talk about why people go to an asylum. And it's because they don't act normal and they don't do what you think they should do. So when we're looking at a square root function, anything grouped under the radical with the x is in the asylum and it's not normal. So on this one, our plus 2 is outside the asylum. So that, first of all, means that it affects the y value. And secondly, it means it's normal, so it will do what we think it should do, which in this case is shift it up 2. So that's our transformation. So we're going to take that parent function that we just graphed and shift it up 2. So instead of 0, 0, I'm going to shift it up 2. And again, what I do when I'm graphing is I think about that t-table that we made and I shift it in my head. So now all of my y values will have a 2 added to them. So instead of plotting 0, 0, I'm going to plot 0, 2, and so on. So 1, 1 becomes 1, 3, and 4, 2 becomes 4, 4, and 9, 3 becomes 9, 5. All right, so now we're gonna take a look at domain and range. The input, again, it's still just the square root of x. So I can substitute any values that are greater than or equal to 0. But my range, because I shifted it up 2, my range shifts up 2 as well. All of my y values are greater than or equal to 2. Now we're looking at, remember with multiplication, that's a stretch or a compression. And we're combining it with a horizontal shift because it's grouped under the radical with the x. So first of all, my transformation is that I shifted not left as it looks because it's negative, but right 4 because it's the opposite of what you think, it's in the asylum. And then the 3 is outside the radical, so that affects the y, so it is a vertical and it's normal, so it's a stretch because it's greater than 1 by a factor of 3. Alright, so first of all, I'm going to think about that parent function and shift it right 4. So instead of 0, 0, I'm going to go right 4. And 0, of course, when you stretch it, stays 0. So then let me do this again real quick so you can remember what I'm looking at. Alright, so now that 1, 1 is also going to be shifted right 4, and the vertical stretch will affect my y value. So what I do here is now that my origin moved, I look at this point as my new origin. And I look at my t-table values as directions instead of ordered pairs. So my 1, that's my x-coordinate right here, is no longer an ordered pair x value of 1. It is right 1 from my new origin. All of my y values, I'm going to stretch or multiply by a factor of 3. So if you're a visual person and you can't keep track of all of this shifting and directions and multiplication in your head, go ahead and jot down your new t-table. So from my new origin, again looking at my first ordered pair here, I'm going to go right 1, and then instead of up 1, I'm going to go up 3 from my origin. So here's my origin. I'm going to go right 1, up 3. So now this one says from my new origin, right 4, up 6. And I'm having trouble counting. Here we go. And from my new origin, I can't go right 9 with the size of my graph. So these are the points that I have. So looking at my domain now, notice that I'm not starting on the y-axis. I'm starting at 4 because you have to look at what's under the radical being greater than or equal to 0. What's under the radical has to be greater than or equal to 0. So when we solve that, we get our domain. The range, in this case, I didn't shift it up or down, so my range is the same as the parent function. All right, last one. Let's take a look at what happens. Oops, sorry, I missed my square root. Now I'm trying to think where I wanted that to end. I wanted that to end here. So just the 2x's under my radical. And the -3 is outside the asylum. So we're looking at 3 different transformations here. The first thing that I did was, and the 2 is inside the asylum, so it is not a horizontal stretch, it's a compression. Sorry, I didn't label it. It's a horizontal compression of 2. And then the negative on the outside reflects. And think about this. I'll come back to it. Think about which axis that reflects across. If it's outside the asylum, does that flip across the x-axis or does it flip across the y-axis? And then my -3 is outside the asylum, so that's down 3. And for the answer, it reflects across the x-axis. Because what it does is it affects the y value, and the y value tells you to go up or down. So instead of being a positive y value, it will now be a negative y value, which reflects across the x-axis. So I'm going to jot down our parent function values again. And think about all of these different combinations of things that we're doing to them. So first of all, compressing 0 by 2 will not affect it. Reflecting it across the x-axis won't affect it, but I am shifting it down 3. Alright, so now my second ordered pair, it's a horizontal compression of 2, which means I'm shrinking it. So I'm multiplying my x values, which remember I'm now thinking about as direction, by half. So I multiply all of my x values by half because I'm compressing it horizontally. And then my y values, yes, they're going down 3, but I'm thinking about them as directions now. So I'm going to look at it as the same direction from my new origin, and the down 3 will be taken care of. And then the reflecting across the x-axis means instead of moving up, I'm moving down. So you can think about these directions becoming negative now instead of positive. So from my new origin, I'm going to move over half, right half, down 1. And notice how that minus 3 is taken care of because I'm not down 1, I'm down 4. So that minus 3 is built in with looking at it as my new origin. From my new origin, I'm going to move right 2 down 2. And from my new origin, I'm going to move right 4.5 down 3. Alright, so there is my new square root function. Sorry, my calibration's off. I literally just recalibrated it before I started this lesson. Finally, looking at domain and range. Again, what's under the radical must be greater than or equal to 0. So dividing by 2, I still have my domain greater than or equal to 0. And my range comes into play with that vertical and horizontal shift. Vertical and horizontal compressions don't affect the range, only vertical and horizontal shifts. And reflections. So in this case, I've got this shift of down 3, which affects my range, but I'm also flipping it over the x-axis. So as you can see, our graph is moving down from negative 3. So our y value is less than or equal to negative 3 because of the reflection makes it less than or equal to, and the shift is where I get my negative 3 from.